Hello, my name is John Cody. I'm an engineer from Vancouver, Canada. And today we're continuing on with our series of videos on the quadria of the projective quadrangle in universal hyperbolic geometry. Last time, in previous videos, we discussed this quadria of this projective quadrangle given by projective points A1, A2, A3, and A4. And we discovered that it's given by these two quadratic equations in A, where A is the quadria of the projective quadrangle, and Q1, Q2, Q3, Q4 are the quadrances of the sides, and S1, S2, S3, and S4 are the spreads. And what we found was that these two quadratic equations are compatible, and they have a unique solution given by this expression right here. So for a projective quadrangle with projective points in general position, it's given by this equation right here. Now, this it has this equation when this denominator here is not 0. And in this video, we're going to cover the case where this denominator can be 0 or is 0 and what happens in those situations. Okay, so first we'll look at this alternate form of the projective quadrangle, given these two quadratic equations, and we're substituting the quantities Q1, the quadria of the triangles, A1, A2, A3, A4, we're substituting these values with A1, this value with A2, this value with A3, and this value with A4 in the above two equations, and we end up with these two equations. What this says, this equation here corresponds to triangulation of the quadrangle, where there's a chord between projective point A1 and A3, and that divides the quadrangle into two projective triangles, and the quadria of those triangles is A2 and A4. Similarly, this second equation corresponds to this triangulation, where we have a chord between A2 and A4, which subdivides the quadrangle into two triangles with quadrias A1 and A3. So the quadria of the projective quadrangle quadratic equations become A, the quadria of the quadrangle, minus A2 minus A4, that's this quadria of this triangle minus the quadria of this triangle. All that squared is equal to 4 times Q1, Q2, Q3, Q4 times 1 minus S1 times 1 minus S3. The S1 is here and the S3 is here. And similarly, that up here for figure 2 here, it corresponds to this equation, where the quadria of A minus A1, this triangle, minus the quadria A3, the quadria of this triangle up here. All that squared is equal to 4 Q1, Q2, Q3, Q4, 1 minus S2, 1 minus S4, where S2 and S4 is where the chord is triangulating. In that case, the general formula, the unique general formula for the quadria of the projective quadrangle becomes A, the quadria of the projective quadrangle, equals A2 plus A4 plus A1 plus A3, all divided by 2, minus 4 times Q1, Q2, Q3, Q4, 1 minus S1, 1 minus S3, all that minus 1 minus S2 times 1 minus S4, all that divided by 2 times A2 plus A4 minus A1 minus A3. Okay, so what we'll be looking at in this video is what happens when A2 plus A4 equals A1 plus A3, and this denominator becomes 0. Okay, so that's when does this occur? And when this becomes 0, then we cannot use this equation here. So one situation where it occurs is, well, first we'll look at what happens when the spread S1 or S3 is equal to 1. So what happens in this setup here where S1, this spread here, is equal to 1, or this spread up here, S3 is equal to 1, then the right-hand side of this equation becomes 0, and we end up with the equation a minus a2 minus a4 all squared equals 0. So that's right here, a minus a2 minus a4 squared equals 0, or resulting in a equals a2 plus a4. So what that if when you triangulate the quadrangle into two triangles, the chord that subdivides it, where the spread occurs along where the chord exists, like S1 or S3, if those are equal to 1, then the quadria of the quadrangle just becomes the quadria of this triangle plus the quadria of this triangle. And similarly, if S2 or S4 is 1, in this setup here, if S2 or S4 is equal to 1, then the right side of the second equation is 0. And we get this equation here, a minus a1 minus a3 all squared equals to 0, resulting in a equals a1 plus a3. So the first case, when a2 plus a4 is equal to a1 a3, so if we have a quadrangle with two adjacent spreads equal to 1, then we get the condition. Say we have a quadrangle with S1 equal to 1 and S2 is equal to 1. Then in that case, we get A4 plus A2 is equal to A3 plus A1. So the two quadratic equations 1 and 2 are identical, with the right-hand side equal to 0, and we just end up with two linear equations which have common solution A for the quadria of the projective quadrangle. So A is either A1 plus A3 or A equals A2 plus A4 when two adjacent spreads in the quadrangle are equal to 1. So the next case 2, is we have this quadrangle A1, A2, A3, A4, and what happens as we move the point A4 up to somewhere up here? So the quadrant says Q1, Q2, Q3, Q4, and this chord here between N and A3 is Q5. So what happens as this moves up and is on this chord here, then we have the condition that S4, the spread at node 4, is equal to 0. And as it continues to move up, then the spread increases from 0. So we can get this condition where A1 plus A3 equals A2 plus A4 from above. A1 plus A3 equals A2 plus 4. That can occur when S4 is equal to 0, and we have this condition here, and either Q3, Q4, or Q5 is equal to 1. So we'll consider the case where S4 is 0 and projective. So when S4 is 0, the projective A3, A4, and A1 all lie on a line, obey the projective triple quad formula given here. So Q3 plus Q4 minus Q5 squared equals 4 times Q3 times Q4 times 1 minus Q5. This is an alternate form of the projective triple quad formula. If Q5 is equal to 1, substitute 1 into here, then the right-hand side is 0. So we have Q3 plus Q4 minus 1 all squared equals 0. And so we get Q3 plus Q4 is equal to 1. Or Q4 is 1 minus Q3. And since one formula for the in universal hyperbolic geometry for the quadria of a projective triangle is the quadrants times the altitude. So the quadria A of a projective triangle is the quadrants times h, the altitude. We get in the case of when S equals 4 and Q5 equals 1, when we have a spread equal to 0 at S4, and the quadrants between A3 and A1 is equal to 1, then we get the quadria A4 is Q5 times its altitude, which is 0, so that's 0. A2 has a a quadria of Q5 times H, A1 is Q4 times H, and A3 is Q3 times H. So in this case, we have A2 plus A4. A2 plus A4 is Q5 times H, and A1 plus A3 is Q4 times H plus Q3 times H, and that's equal to Q3 plus Q4 times H, but Q3 plus Q4 is equal to Q5. So we find that A2 plus A4 is equal to A1 plus A3 when S4 equals to 0 and Q5 is equal to 1. We get the same result when either Q3 is equal to 1 or Q4 is equal to 1 or Q5 is equal to 1. So in this arrangement here, if Q3 is 1 or Q4 is 1 or Q5, the quadrants between A3 and A1 is 1. If for any of those cases, then we get the same condition. So notice what happens when the pair of quadratic equations of the quadria of a projective quadrangle, here they are, A minus A2 minus A4 squared equals 4 times Q1, Q2, Q3, Q4, 1 minus S1, 1 minus S3. And the second equation, A minus A1 minus A3 all squared equals 4Q1, Q2, Q3, Q4, 1 minus S2, 1 minus S4. Substituting S4 is equal to 0, and when Q5 is equal to 1, we have these two quadrias equal to these two quadrias. In that case, we divide equation 1 by equation 2, and we get, so the left, for these two equations here, if A2 and A4 are equal, and A2 and A4 is equal to A1 and plus A3, then the left-hand side of both of these equations is equal. The quadrants is Q1, Q2, Q3, Q4 of both of these are the same. S4 is equal to 0. So if we divide what remains of these two equations, we get 1 minus S2 equals 1 minus S1 times 1 minus S3. And we note that this is the dual of the projective Pythagoras formula in universal hyperbolic geometry, when the quadrants between projective points is equal to 1. So from our pair of quadratic equations, we are getting the projective, if we take the ratio between them, we get the projective Pythagoras formula. I'll also mention that the projective Pythagoras formula also emerges under the condition when we have projective quadrangle where two adjacent spreads are equal to 1 and the quadrants between them is equal to 1. So in a previous video, we showed that the quadrangle with adjacent spreads equal to 1 and adjacent quadrants to these spreads equal to A, B, and C, then the quadria of the projective quadrangle is given by this formula. A equals AB plus BC minus ABC. So what that means is if we have a quadrangle with 4 points and two adjacent spreads, so let's say this spread at this projective point here and this spread here is equal to 1, and the side let's say it's A, B, C, the adjacent quadrangles, then the quadria of that projective quadrangle was shown in a previous video, this formula. So what happens when the quadrant B is equal to 1? This formula here becomes A equals A plus C minus AC. And we note that this formula looks like is the same formula as the projective Pythagoras theorem in universal hyperbolic geometry given here. So in universal hyperbolic geometry, the projective Pythagoras theorem says C is equal to A plus B minus AB, and we're getting the same thing here, A plus C minus AC is equal to some quantity. So we've shown that the projective Pythagoras formula appears as a consequence of setting the quadrants between projective points equal to 1. Okay, and the last case where triangular quadrias A1 plus A3 is equal to A2 plus A4 can occur when we have 4 projective points all lying on a circle, and the chords of these 4 projective points meet at the center of the circle. If that's the case, then we have this condition A1 plus A3 equals A2 plus A4. So let's see what happens in that case. So what happens is the spread S between these two diagonals. So again, we have projective points given in red here. These 4 projective points form a circle. They all lie on the circle, and the chords, these 2 chords, meet at the center of the circle, and the radius of the circle has quadrants P. So this, from this point here to this point, is the quadrants P, similar from here, from center to here, and center from here to here, and the center from here to here, all have quadrants P, let's say. So what happens in that case? So this spread between these 2 lines is S, so that spread is here is the same as the spread here, it's the same as the spread here, it's the same as the spread here. The spread is just a spread between 2 lines. So we have 4 triangles here, and the quadria of these 4 triangles is identical. It's P times S times P. P times S times P. They're all P times. So the quadria of this triangle is equal to the quadria of this triangle. Give these 3 points is the same as the quadria of this triangle by these 3 points. It's the same as the quadria of this triangle by these 3 points in the center of the circle. So all the triangles A1, A2, and A3 and A4 are composed of 2. So these are smaller triangles. These 2 triangles here, for instance, they have identical quadrias, and this triangle, bigger triangle here, is composed of these 2 smaller triangles. The 2 triangles on either side of a chord, so this chord here, a triangle right here, and a triangle right here, they're both composed of 2 smaller triangles which have identical quadrias. So it follows then that the triangles with A1, A2, A3, A4, these triangles on either side of a chord, are all identical. So they'll have A1 equals A2, A equals A3 equals A4. So it follows then that the 2 quadratic equations 1 and 2 from the beginning of the video are the same. So the quadratic equations become A minus A1 minus A3 all squared, that should be a squared there, is equal to 4 times the quadrants of the sides. So 2 of the quadrants are A and B. So you get 4 times A times B by times B times 1 minus S2 times 1 minus S4. And by symmetry, we have 1 minus S2 is equal to 1 minus S4. So let's say this is S2 here and this is S4 down here. They are identical symmetry. And we get A, quadria A of the projective quadrangle minus A1 minus A3 is equal to, without the square now because we have squares on both sides, is equal to 2 times A times B times 1 minus S2. And we note that A1 equals A2 equals A3 equals A4, and that A2 is, let's say, A2, if this is point 2 up here, A2 is the triangle here from from these 3 points. So that's A, the quadria of that triangle is A times B times S2. That's the spread at point 2 there. And so we end up with, since A1 is equal to A3, we have A minus 2 times A1 equals to 2 times AB minus 2 times AB times S2 was A2. So we have, bringing this to the other side, we have A equals 2 times AB plus 2 times A1. When we bring that to the other side, we have 2 times A1 minus 2 times A2, but A1 is equal to A2, so these two terms cancel, and we end up with the quadria equals 2 times A in the situation where the 4 points of the quadrangle lie on a circle, and the meat of the chords of the circle go through the center of the circle. And that's stated here. So the quadria of the 4 projective points on a circle forming a rectangular shape with side quadrants A, B has quadria equal to quadria A of the projective quadrangle is equal to 2 times A times B. So that covers that situation. Okay, thank you for listening.